Okay, great. Next we have Songlin Jia. He's going to tell us about Typestate via revocable capabilities.
Thank you. Hi, everyone. Thanks for coming. I'm Songlin from Purdue University, and this is Typestate via revocable capabilities, joint work with my great collaborators. So first, what is Typestate? In simple words, Typestate means tracking the state changes of objects the same way we track types, statically at compile time. The classic example is locking. Languages like Java offer implicit lock management tied to lexical scopes. That's simple to use, but lock lifetimes are then forced to nest, so you cannot release a table while still working on a row. In contrast, by using lock and unlock methods directly, imperative code allows us to unlock the table as soon as we lock the row. So that's hand-over-hand locking, which offers better parallelism. By type-state tracking on locks, we can further statically ensure that we never use resources without locking them. The next example is about building DOM trees. A tree is well-formed only when all tags are properly nested. The state we track is no longer a simple flag, but the entire stack of currently open tags. Here, we demonstrate the checker catching two possible errors: closing a tag that doesn't match and closing when no tag is open at all. The tidbit here is that Typestate is not limited to a finite set of named states. It can track structured states like the stack and use it to enforce grammar-shaped invariants entirely at compile time. Our last example is about communication protocols, or session types. The two ends of a channel must follow a protocol, a predefined sequence of sends and receives, and crucially, that protocol keeps evolving as the program progresses. In our example, the server keeps receiving strings until the client decides to quit, and only then closes the channel. Don't worry about the exact state transitions here, but the point is that we must track the channel state statically, even through recursion and branching. So we've just seen three quite different examples: logs, documents, protocols. In this work, we try to provide a single mechanism that covers all of them: revocable capabilities. Let me walk you through how it works. As a running example, you may only read or write a file when it's open. There are really two ways to write such code. First, in the direct style, you just call open, write, and close as you go. To make that safe, you need full type state, and people have already explored this for a very long time, from early whole program analysis to type-state-oriented languages like Plate and session types. But the existing solutions tend to come at a price. They are tied to specialized languages or specialized domains, or they impose restrictions on aliasing using mechanisms like linear types and fractional permissions. Alternatively, in the scoped style, you wrap the file in a with file block, and now the only thing you need for safety is to ensure that the capability F doesn't escape the scope. That's a much lighter requirement, and several proposals have been made recently: second class values, reachability types, and Scala's capturing checking, the last of which is already running inside a mainstream language. So the natural question is, can this lightweight capability-based path be generalized to express full type state? Our answer is yes. Without inventing a whole new type system for Scala, we can describe stateful methods like open using a single signature, where that funny arrow in the middle explains the process. Reading it left to right, it does three things. It receives the closed state capability, revokes it to stop further use, and returns a new open state capability. Our receiving mechanism simply reuses Scala's implicits. Revoking requires an effect system that builds on reachability types and capturing checking. Returning a capability is our new extension and is implemented via a simple transformation. To see why this setup is necessary, let's build it up naively first. The simplest encoding is just to use different types for different states, an open file and a closed file as distinct classes. A new file is always closed. Open converts that file to an open file, and close goes the other way. Crucially, read and write require an open file. So already, the type checker guarantees that you can only write to an open file. The naive version already gets us a lot, but it has three serious problems. First, after close gives you a fresh closed file, The old fopen handle is stale, but nothing stops you from writing to it. Second, if you open file A, the resulting open file doesn't actually remember it's A, so you might accidentally write content meant for B into A. Third, because every operation returns a new handle, you are forced to thread a chain of freshly named variables through your whole program. These 3 pain points motivate our 3 pillars. Flow-sensitive revocation kills the stale handles. Path-dependent capabilities tie a capability to its object. And flow-sensitive implicits remove the naming burden. We detail these pillars in the next couple of slides. Pillar 1, flow-sensitive revocation. We annotate close with a kill effect on f, meaning that argument f is consumed. After calling close fopen, any later use of fopen is flagged as using a killed capability. That fixes the stale handle problem. The interesting part is doing this under aliasing. We use what we call descriptive alias tracking. We track sharing by names, so we impose only the minimal restriction. Such mechanisms include reachability types and capturing types, where destructive effects have been proven summed in the context of reachability types, and we build our revocation mechanism based on the experimental capturing type checker in Scala. The example below demonstrates such tracking. FC may alias with either FA or FB. When we close FA, the checker knows FC could reach the killed FA, so writing through FC is correctly rejected. Pillar 2, path-dependent capabilities. Instead of using different types for different states, we made capabilities abstract type members of file objects. So every file has its own isClosed and isOpen types. Then, using path-dependent types from dot, the calculus underlying Scala, a capability of type f.isClosed is provably about the file f and no other. So open takes the object f, and separately the isClosed capability C specific to f, and then kills only the capability, not the object. This path dependency is immune to kill effects from pillar 1, and it gives us a guaranteed link between the capability and the object it governs. So a write does not silently go to the wrong file. Pillar 3, flow-sensitive implicits. This improves ergonomics. Half of it is already in Scala. Instead of passing the capability by hand, we mark it with using, so the compiler finds the nearest implicit candidate, and you just write openf. The new half that makes implicit really flow-sensitive is a returning. The treat here is that when a function returns both the data and the capability as a dependent pair, or we call it sigma, our inf transformation kicks in and extracts the second component as an implicit candidate for the rest of the block. So after assigning the result of new file to f, the isClosed capability is silently available, and the next open just picks it up. No more threading chains of renamed variables. The program reads like ordinary imperative code. Putting these 3 pillars together, here's the payoff. We support all our motivating examples with the same mechanism implemented in Scala. The file operations now read top to bottom on a single variable f. The same mechanism handles hand-over-hand logs, building well-formed DOM trees and binary session types where recursion and branching exist. Now, what this buys us in real control flow and what it costs. First, the easy case is when control flow doesn't fork the ending state. Using a capability repeatedly needs no special treatment at all. Here we write to f inside an ordinary for loop, where each iteration leaves the state unchanged. Likewise, a plain if then else is fine as long as both branches land in the same state. In this session types snippet, both the then branch and the else branch fully execute the protocol and closes the channel. So we just use a normal if. So the takeaway is a lot of real code needs 0 extra work. The harder case is when branches end in different states. We handle this by reifying the choice as either capabilities, and we offer combinators to work with them. Our if combinator runs one branch, for example here, leaves the file open, and another branch that leaves it closed, and its result is either of is open and is closed. the state becomes data. Joining is a duality. A matched combinator inspects that either implicitly, and in each case, the capability is recovered with the right state. So both cases can now converge here back to being closed. Combining fork and join gives us state-dependent loops. The while combinator here, for example, keeps iterating until the ending state is reached. The iterator is exhausted. So even non-trivial control flow stays expressible and checked in our framework. What does it cost? We measure the DOM tree examples, and the key message is the overhead of capturing, checking, and our effects is comparable to the compiler's other phases. It's not a blow-up. On the left, the ablation at fit steps of 17 shows that capture, checking, and effects contributing a reasonable slice over the baseline. On the right, stating the depths from 17 to 33, the effect phase grows, but stays in the same ballpark as typing and the rest. So the approach is not only clean, but also practical. To wrap up, we bring Typestate to Scala and to general settings by treating stateful programming as receiving, revoking, and returning capabilities. We get ergonomic control flow and impose only minimal aliasing restrictions. Our three pillars include destructive effects for revocation, path-dependent capabilities for tying state to object, and the new ingredient is that implicit return values while NF transformations. We validated our framework on files, logs, DOM trees, session types, and control flow combinators, and our artifact is available online. Thank you very much. I'm happy to take any questions.
Okay, thank you very much.
Hi, thanks for the talk. Big fan of capabilities. I wonder if you can speak about the revocation aspect and what that's doing for you here, and whether this is a mechanism for something like consuming a linear resource, and how you are you thinking, or like how are you doing session types within this context of Scala, and are you thinking of doing linear typing with this, and are you able to recover this from these mechanisms? Thank you.
Yeah, great question. So of course, revocation would naturally make people think about linear types, and naturally you can do some type-state programming in linear types. But the point of what we are doing here is that, so revocation or moving resources or moving capabilities or consuming them should be optional. So later in this talk, I showed an example like you can summon or using capabilities in a loop. So that does not constitute any of the usages or consuming at all. So that's simple using. Whereas only for such, when we are really invoking a state transition, we must want to consume that capability for someness. So our revocation here, you can think of understand it in the way similar to linear types, but consuming is only optional in our setting. That's for the first question. For the second question about session types, let me see if I can get to the example. Yeah, so here, so basically we have to annotate, we have to track the protocols, session type protocols basically, as a abstract type member, like I said, in some field of the channel protocol. So basically, you can think of this as a real type signature for this. For example, the first red push is like, it is transitioning the channel.ptab. So ptab is a capability type, and ptab is parameterized over this red receive you are really seeing. So that's the session type. Yeah, hope this makes sense to you. Any other questions?
Okay, let's thank the speaker again.
Thank you.